Okay, so welcome everybody. Today our speaker is Kailash Sahu. Kailash did his PhD in 1985 at Gujarat University. Later he was support astronomer at Instituto de Astrofísica de Canarias and research associate at ESO. It was more or less in 1994 when he published a paper saying that the microlensing events we observed toward the Magellanic Clouds have lenses most probably in the Magellanic Clouds themselves, not in front of them. Since then, Kailash was involved in different kinds of microlensing studies. He also led HST program, which showed that gamma ray bursts are associated with an external galaxy. He also studied transits and proper motions from HST towards the galactic bulge. And today he's going to talk, I guess, about the white dwarf astrometric microlensing, which was a great thing published in 2017. Kailash, the floor is yours.
Okay, thank you. Thank you. I'm very glad to be able to speak about microlensing in one of the best known microlensing centers. You guys actually, without you, there would not have been any such huge microlensing field as it is now. So I'm glad to be able to talk here now. So I want to talk about mainly about astrometric microlensing and about two different things, the mass determinations of isolated white dwarfs and detection and mass measurement of the first isolated black hole through astrometric microlensing. I have trouble switching. Okay. As I said already, okay. So to give you a little bit of introduction, the general relativity, Einstein postulated his general relativity in 1916, which was experimentally confirmed by Eddington through the observation of the deflection of starlight during the 1919 total solar eclipse. Now, the 1919 solar eclipse, during that time, the deflection caused by the sun is about 1.75 arc seconds. So that was just about possible at that time. 100 years later, we can actually use that technique to measure astrometric deflections by outside the stars outside the solar system. And trouble in moving the next slide. Okay, so now the gravitational bending can be used as a tool to measure the mass of a star. Now, the mass of a star is probably the most important parameter of a star. The mass determines its pretty much everything, what is the radius, what is the temperature, how long it will live. Everything is decided pretty much by the mass of the star. Yet, we astronomers do not have a technique to directly measure the mass of an isolated star. We can only measure if it is in a binary or something like that. So, the deflection, the astrometric deflection tells you the mass directly. But of course, the expected deflections are pretty small. It's about 1,000 times smaller than what Eddington measured in 1919. So it has not been measured. So I wanted to talk to you first about the very first the astrometric deflection measured by a star outside, by a white dwarf outside the solar system, though it works like this as it is shown here. So several years ago, I tried this technique. We used, at that time, even Gaia was not available, used all the proper motions of all the high proper motion stars and see whether it passes close to another star. Here you can see 1992, the top, you can see the image taken in 1992, and the bottom, you can see the image, DSS image, ground-based image taken in 95, which shows that this white dwarf would come close to the this background star in 2013 or so. So we proposed to observe this with HST, so that it works like this. So as the foreground white dwarf now passes close to the white dwarf, it passes close to the background star, it deflects the light as it is depicted here. So again, for white dwarf, as it passes by now here, the background star gets deflected, makes a circular motion, and that is, if we measure that, that gives the mass of the white dwarf directly. Now, why white dwarf? There, all stars with mass less than 8 solar mass, they end their lives as white dwarfs. Now, there is a mass-radius relationship, which is a fundamental relationship of white dwarfs, directly from the electron degeneracy theory, and that predicts a clear prediction of mass radius. The available data at that time was given here. As you can see, the measurements are all over the place. Maybe they follow, but it was not very clear. In particular, what happens, all the measurements were for binary of white dwarfs, and whether they are affected by the mass transfer or not, whether they follow or not. It was pretty clear, but there were still some doubts. Particularly the one, the Stein 2051b had been controversial. I won't go into all the details because I have to cover the black hole part, which I wanted to spend more time on. So the Stein 2051b, this is the 6th nearest white dwarf. And it's a binary, but the Stein 2051b itself is pretty isolated. It's not affected by the companion, which is on more than 55 astronomical unit away. So this provided an opportunity to measure the mass of Stein 2051b via the relativistic deflection. So here is what we measured. We predicted the path. Here, once we had the very first HST observation was taken in 2013, and once we had that, we predicted this motion, taking the parallax and the proper motion into account, and appropriately designed the observations. And here are the 1, 2, 3, 4, 5, 6, 7, 8 observations taken. And here, this is again shown here as so. This is the actual HST observations as it passes by. This is the first one, second, third, fourth, fifth, sixth, 7th, and 8th epochs observations. You can see there are some background stars which are not clearly seen here now. Background stars, of course, are fixed. The background star, itself here, the one that would be lensed, is shown here as source, and this passed by. As it passed by, it deflected the position of the background star, which we measured with HST. Now, with as I showed you, as I told you, the deflection itself is pretty small, about 1 milliarc second. That's what we'll measure. Now, I just want to give a feel for what this 1 milliarc second. Of course, Gaia measures this pretty regularly, so I want to give a feel for what this 1 milliarc second is. Now, here it is. Here you are. This is Warsaw here in Poland. You are here. And let's say here is a euro. If I were with you, I would have taken out a euro and shown you. But now here is a virtual euro. And let us see how far, where you are, how far do you have to move this euro, so that this euro coin, so that it subtends an angle of 1 milliarc second. Any guesses where we have to go? So let's see. So how far do we have to move? All the way to Mumbai in India. That's where the euro has to move. I happen to be just returning from Mumbai, so just put this here because that's the correct distance. I came back the day before yesterday. That's why I was it was difficult because I had a personal loss and I had to travel. But so that's why I was rushing to prepare this talk. But anyway, so here you are here in Warsaw, and the euro, the coin is in Mumbai, as you see here now, and the angle from one side to the other is 1 milliarc second. So suppose there is an ant or a little insect which is there in Mumbai, and it moves from one end of the coin to the other end of the coin. That's what you have to measure very precisely. And in this particular case, there is a white dwarf. You have to measure the position of this background star in presence of this very bright white dwarf. So that's the difficulty. And that's why it was never done. But we were able to do this. So this was actually challenging, but we had to correctly subtract the white dwarfs PSF. In fact, this was a very useful exercise for our black hole project that I can show you. The black hole project where also there happens to be a bright star, and we were prepared to actually correctly subtract the PSF because we had this already, the technique how to do this. Anyway, so the source here is 400 times fainter than Stein 2051b. So it's let's say a firefly next to a 100-watt light bulb, and we measured this position. And here are the actual measurements. The epoch 1 is here is the line here that shows the undeflected positions. The deflected position is here. So the deflected position here in the epoch 6, for example, is the largest, and epoch 7, epoch 8, and the XY deflections are in epoch 1, 6, 7, 8. We had to, the few of the 1s, 2, 3, 4, 5 actually were so close that we could not actually measure. It was extremely close to the white dwarf itself. So we could actually measure only 4 epochs, the actual positions. So here are the deflections, and only the white dwarf, only the background star near the white dwarf showed the deflections. The all other 26 reference stars showed no such motion, and that suggests that the Einstein ring is 31 milliarc seconds. The mass comes out to be 0.675. And this falls exactly in the mass-radius relationship. It exactly falls on the mass-radius relationship. As I said, this was a bit controversial. Some people had said, well, this could be an iron core, and the mass may be here. And nobody knows how to make an iron core white dwarf. So it was pretty clear that it's a normal white dwarf and follows the mass-radius relationship. And so here it is again, which confirms the white dwarf evolutionary theory. Now, of course, this was covered in many newspapers and all that, but one that which I really liked was this was also rated as one of the 100 best science results of that year. So we are following the same project. The next one is astrometric microlensing by a real isolated white dwarf, Lord 37. It is similar. Again, the HST observations are shown on the right here, and the deflections are here again, the deflections and the fitting of the light curve, which shows the mass of this is about 0.56, which again falls exactly on the mass radius relationship. And we have one more with JWST. JWST is expected to provide an astrometric accuracy about 10 times better, not because the astrometric accuracy itself is higher, but the background star becomes much less problematic with JWST. So we can measure actually the astrometry much better. So the accuracy of the measurements would be even higher. So we have one JWST observations coming up. One observation has been taken. So this is being continued. Now, I want to move to the black hole part. So this is, I think, it has consumed me for the past couple of years at least. Now, to give you a little introduction, all the stars which start with a mass more than 20 solar mass end their lives as black holes. So people have done calculations. Well, Vukas has done a lot of work on this as well. So the prediction is that it should be about 100 million black holes in the galaxy. People have taken the mass function, and if you take all the masses of all the stars with mass larger than 20 solar mass, then how many there should be? There should be about 100 million. Now, I want to give you an idea of what 100 million is. Now, 100 million, suppose you put the 100 million stars in the sky, say uniformly, there could be more concentration to the disk or so, but in any case, let's put uniformly. Then as you look at the moon or the sun, behind the sun, there should be approximately 600 black holes. So black holes, 100 million everywhere. There are lots of black holes. And out of these 100 million black holes, a large fraction of these black holes are expected to be actually isolated, because in the massive stars, if you take the statistics of massive stars more than 20 solar mass, about 30% of them are already single. 70% are in binaries, but 30% are already single, which will end up as single black holes, of course. So 30% out of these 100 million, 30% are single because they start out as single. Now, among the closed binaries, if the binary is close, then during the supernova explosion, they can lead to the merging during a supernova explosion, leading again to a single black hole. If the binary is wide, then there would be a kick velocity. The asymmetric explosion is supposed to give a kick velocity to the black hole, which would cause the orbital separation, and that will lead to the formation of a single black hole again. So out of these 100 million black holes, a large fraction should be single, but not a single such isolated black hole had ever been detected. All the black hole detections had been in binaries. So most of the galactic black holes are from these X-ray binaries, and then radial velocity of this companion then tells the mass of the black hole. Recently, actually, there have been at least one where you might have seen that one at 140 parsecs. That was actually not through X-ray, but through Gaia observations of the wide separation. The separation is wide enough that there is no X-ray emission, but the astrometric motion shows that the companion is a black hole. So black holes also, of course, have been detected by LIGO. Many such merging black holes have been detected by LIGO, which are shown here. So now the masses of the black holes in binary in our galaxy have been mostly in the 3 to 20 solar mass range. There have been some claims that there may be a mass gap or not, but so anyway, the masses in our galaxy, they range from 3 to 20. Theoretical models, they have been changing, but the theoretical current models, they range from 3 to 80 solar masses. The black holes detected by LIGO, they have masses from 5 to 100 solar mass. So there seems to be some discrepancy here. There might be this may be because of selection bias, but there is some discrepancy now. So the observed masses, of course, have their own biases. So the mass determination of a few isolated black holes may provide some important insight. So we started this HST program to detect such black holes, which may provide unbiased mass, and it may have its own bias, but it would be a different set to determine the mass and velocity distribution of black holes. then some other motivations. So the theoretical models have a lot of uncertainties in what the predicted velocity of the remnants should be. There are models which say that if the initial mass is higher, then the kick velocity would be higher. Then there are other models which say no, the final momentum of the remnant is independent of the initial mass. So since the momentum is the same, higher mass would have smaller velocity. Low ones would have higher velocity. Then there are other models which say no, the explosions in the lower mass stars are actually asymmetric, more asymmetric, causing the lower mass ones to have a very large momentum. So that means the higher mass ones would have very small velocity and the lower masses would have very high velocity. So there is some uncertainty here. So there would be, if we can measure actually the velocities, that would provide some insight. Now, the microlensing is the only technique which is actually capable of detecting such the isolated black holes. And in fact, microlensing can not only detect the isolated black holes, but they can also measure their masses, distance, and velocity, as we'll go through now. So this, I don't need to show this. I was going to remove this, but in any case, so here is a little diagram here which shows that if the lens, here is the red point is the lens, this is the Einstein circle is shown by this black circle, and the green one is the background source. As it passes by, it causes two images, and these two images, one is outside the Einstein ring, one is inside the Einstein ring. One outside the Einstein ring is the one which is brighter. And so the brightness now depends purely on the areas. Surface brightness, lensing preserves the surface brightness. So as it becomes bigger, it actually brightens up. So the 3 points that we need to note here is that the one outside the Einstein ring is always brighter. The lens, source, and the three images and the two images are all, the lens, source, and the images, they're all in a straight line. These are main things that we need to keep in mind as we go through the astrometric microlensing part. I'll see again. Okay. So, of course, OGLE and MOA, microlensing network, they've started this microlensing program since 1993 or so. They monitor millions of stars towards the galactic bulbs and Magellan clouds to look for microlensing events. And the microlensing groups have detected about 30,000 microlensing events so far. Now, microlensing can be by anything. It can be by a star, it can be by a planet, black hole, white dwarf, neutron star, anything. So some of the events, of course, have to be caused by neutron stars and stellar mass black holes if they are out there. Now, the question is, how do we know which ones are the black holes? So one idea is the mass of the lens. If you go through the equations, you see that is proportional to the time scale square. So if from this relation, you would expect that if the time scale is large, statistically, then you would expect the mass of the lens to be larger. But the mass of the lens now depends on 4 different parameters: the time scale, the distance to the lens, distance to the source, and the velocity. And the microlensing light curve only provides one single useful parameter, which is TE. So the mass estimates from time scales, from pure photometry, are statistical. So the long duration events can also be caused not only by the high mass objects, but they can also be caused by slow moving low mass objects. If the velocity is low, then the time scale can also be larger. That has been the main problem why photometry itself is not enough to tell whether the lens is, to determine the mass of the lens. So now astrometry can break this degeneracy. The amplification at any given time depends purely on the lens source distance, the unit of Einstein ring radius. The astrometric shift depends on two things: the U, which can be determined from the photometric curve, from the amplification, and it depends on theta E. So if you measure the astrometric shift, it gives you an idea of what theta E is, what the Einstein ring is. Now, once you know the Einstein ring radius, that Einstein ring radius is given by these parameters, the mass and the distances. Now, we have got rid of the velocity, which was the main uncertainty. Velocity was the one that can change by a large factor, and that's the main problem. So now here, the astrometry, once you get the astrometric shift, it gives you the Einstein ring radius, which depends on the mass and the distances. And so if we can measure the astrometry and the distances, we can determine the mass. So the astrometric shift now provides a measure of the mass as a function of distances. Now, just quickly how the astrometric microlensing works. So here it is. Again, you must have seen this. Lucas might have shown you this already. This was made by Scott Gowdy. So this is here, again, the lens, the Einstein ring radius is shown by this green circle, and the red open circle is the one that passes, is the source which passes through this Einstein ring. As it passes by, then there are two images that are shown in blue, and the one that the blue outside image is the brighter one. So the centroid shift now is shown by the red solid circle, since the outer one is brighter. Now, this entire thing is of the order of milliarc seconds. So we don't see the individual images, but we see only the red one here, how it passes by. So it moves, it does not move exactly in a straight line, but there is a deviation, which is the characteristic of this microlensing, which we need to measure. Now, so as we saw, the astrometric, once you get the astrometry, that tells you the mass as a function of distances. Now, if the microlensing time scale is large enough, then during that time, the Earth's motion around the sun introduces a distortion on the microlensing light curve, and that parallax provides an estimate to the distance to the lens. So the distance to the lens you can measure from the parallax measured from the light curve itself. Then the distance to the source, you can, most of the time, the source is, when the observation is towards the bulge, is in the source, is in the bulge itself. 95% of the sources are in the bulge. But the position of the color magnitude diagram, the position of the source in the color magnitude diagram can also tell you whether it is in the bulge or not. But if it can be even better, if there are spectroscopic observations which can be used to type the star, and then the luminosity tells you the distance measurements. So the distance to the source can be measured through several ways. The best would be through spectroscopic observations. So if we can have that, then we can have the distance to the source and the lens, and then astrometry now tells you the mass of the lens. Okay. So, okay, I think I've covered the basics, I hope. So the astrometry gives the size of the Einstein ring, which provides the measurement of the mass, distance, and the velocity, all from a single technique. Now, the method. So the method is we observe microlensing events with long duration. Of course, we expect the high mass objects to have long duration, but it will also, if it is a black hole, then, or a neutron star, then there should not be much light from the lens itself, so there would be no blending. And so we take the long duration microlensing events with no blending, and then we observe astrometrically to determine its mass and see how many of them turn out to be black holes. Conceptually, of course, this is very simple, but as I showed you previously, the deflections are of the order of milliarc seconds, which is not easy. But with HST, it has been demonstrated enough. Milliarc second astrometry is possible. So we started in 2009 or 8. We started the HST program to observe events with relativistic deflections. And we have monitored 8 events so far. The thing is, this takes a very long time. To start with, the time scale is of the order of more than a year sometimes, and we need to observe for at least 5 Einstein time scales, at least 5, or 7 or 8 is even better. So that means we need to observe for 7-8 years. And during that time, the HST data becomes public, and so it causes its own problems. But anyway, I won't go into that now. So the one I want to go into the details is the one where we actually detected the microlensing event is the OGLE 2011 BULS 462. This is the light curve. This is the combined light curve of all the ones shown here: OGLE, MOA, WISE, Danish, and this was a very high amplification event. So it was monitored very frequently, particularly during the peak, because it's sensitive to detecting planets, which was very useful to actually rule out that this object is a part of a binary. So we observed with HST. So the first observations was a few days after the peak. So this is when on the top left, you see, this is when it was brightened by approximately a factor of 12. And then in October, it dropped down. It was only maybe a factor of 2 or 3. And then slowly it came back to its usual brightness after 6 years. So we observed at 8 epochs. And this particular one, we had to measure the astrometric deflections, and one of the challenges was this: there is a bright star close to it, which is approximately 20 times brighter than the source star itself at its baseline. But we were pretty much ready, in the sense I showed you previously the white dwarf was close to a bright star which was 400 times brighter. So this was much less problematic, much easier than the white dwarf one, for example. But we knew how to actually correct for that. So we had all the technique and the procedure developed. And that came out to be a very crucial, actually. So one of the things, when it first happened, as I told you that I wanted to observe only the ones which did not show blending. But actually, it's this particular one, since there is a bright star close by, it showed a pretty strong blending. I have been in this business for a while, so I knew that a lot of the times there are stars just close by and they can cause blending. So we took a chance. We thought, okay, we will observe this. We'll continue observing. And as it came out later on that there was actually a astrometric shift observed from ground-based observations itself, not because of the astrometric shift caused by lensing, but because there is a bright star close by, and this left one, as it became fainter, the light shifted towards the brighter star. So that showed that there must be another star close by. And of course, HST observations clearly showed, yes, there is another star. So we monitored this. And so here, there are, I wanted to show a little more go into some depth of how the PSF causes problems and how we have tried to solve this. So here is the bright star, close the nearby bright star, and the source, location of the source are, and we observed at 8 different epochs. In 6 different epochs, the location of the source is here, and in 2 other epochs, this is E5 and E10, this location is here. These are close to some other peaks in the point spread function. As you can see here, I'm showing you during one single orbit how the PSF changes. So this is a single orbit, and the PSF, the point spread function, HST point spread function, has a breathing characteristic, and that changes. So if there is a source just next to it here, then it can change depending on how the PSF varies. So there is, I'll show you a little bit, but there is another group who tried to measure this, but they just showed, okay, there is one, the PSF that they used, but that's not good enough actually to measure this, because the PSF changes, and which affects the position of the source differently at different images, in different images. So making a single correction for an entire orbit, it does not work. As you will see, it gives wrong results. So here, this is the 8 epochs of observations. Here you see the original images on the top. After the subtraction, we had to subtract the PSF, and the PSF particularly we made sure that at the location of the source, which is on the left is the source, at the location of the source there is no residual from the bright star. And then once we subtracted, we measured the positions of this source star, and it came out to be very critical. We showed that if you don't do, then we haven't gone into we have to publish this in more detail, why it becomes insufficient if you don't take the PSF correctly into account. Anyway, so HST observations were taken in 2 filters, the V and in I, 606 and 814. And the photometric light curve seemed pretty achromatic within 0.02 magnitudes. And this provides strong constraints on the blending. The blending has to be less than approximately 2%. So here are the HST observations spanning 6 years. So the actual position of the source here. So here, the first epoch, second epoch. I hope you can see my cursor. I have tried to make this cursor as big as it was allowed. So here you see the location of the source. Instead of moving in this undeflected position, it would have been in this black line. It moved on this path here. So since we know what the undeflected path should be, now the deflected positions are here, which means we can tell where the lens has to be, because the lens has to be along the line joining. Remember what I showed you in the beginning, along the line joining the lens, the undeflected source and the deflected source along that. And so here, the lens would be here. So the path of the lens is shown by this magenta line here. So this is the path of the lens. The lens moved this way, and the source, which would have been the black line, would have been the undeflected path of the source. It got deflected, and it is shown here. Then here, once we subtract the proper motion, so this is, of course, the black line is the proper motion of the source itself. Once we subtract out the proper motion, here is the actual deflections now. So the deflections, the X deflections and the Y deflections are shown here. In fact, this was stunning for me. I mean, it's when after Jay did this, all the measurements, I fitted this, and it just fits beautifully. I thought, wow, it almost fell on the floor. This is the Y deflection, the X deflections, they follow exactly how the microlensing predicts. Here, you don't, there is only a couple of parameters that you can change. The location of the maximum deflection is at 1.4 Einstein ring radius. So only thing that we can change is the Einstein ring radius and the path, and that's all we can change. And once you do these two, they fit all the X and Y deflections fit the observations beautifully. So this suggests a theta e of about 5.2 milliarc seconds, and these are the proper motions. Now the light curve now tells the pi, the parallax, which tells the distance is about 1.6 kiloparsecs. So once you know the distance to the distance to the source was measured through spectroscopy, that this was a very high amplification event. So at that time of peak amplification, this was measured, spectroscopically measured. We used that to do a spectral classification, and the distance came out to be about 6 kiloparsecs to the source. So the distance to the lens is 1.6 kiloparsecs. And once you know the distance to the source and the lens, the mass comes out to be about 7.1, plus minus 1.3 solar masses. And then since we know the time scale, the time scale and theta e, now that tells us what the transverse velocity is, which is about 45 kilometers per second. Now, so this is the, so since we know the distance to be about 1.6 kiloparsecs, we use the Gaia to see all the stars at 1.6 kiloparsecs, what kind of proper motions they have. So around 1.6 kiloparsecs, these are all the stars, and they have the proper motions. Their proper motions are shown here. There seems to be two different, in the CMD, the two sequences, and then those are shown by the blue and the red circles. So these are the actual proper motions of all the stars, and the black hole, the lens, is here, which seems to be clearly an outlier. And from the peak of this, the velocity is about 45 kilometers per second from the mean motion of the stars in that neighborhood. So, so this is a lens has a 7-point solar mass star at 1.6 kiloparsecs, which is moving at 45 kilometers per second, which we still do not know, let's say, what the nature of the lens is. Now, we know that it moves at 45 kilometers per second, and we have observed this with HST for 6 years. So that means we can now see in 6 years what the location of this lens should be. So here is the PSF, and at the 2017, the location of the lens would be here. Okay, so we put if the lens has a brightness of about 1% of the source itself, it would have been detected. So this is a 7-point solar mass star, the brightness of which is less than that of a 0.2 solar mass star. So that cannot be anything but a black hole, since we know the mass to be 7-point solar mass and the luminosity to be less than that of a 0.2 solar mass star. So we detected so this is clearly a black hole. Of course, as I told you before, this particular event was monitored pretty frequently around the peak, so which rules out that the lens could be a binary. So it's an isolated one; it cannot be a binary. So it's there cannot be any companion up to about 200 AU. So this is a isolated black hole at 1.6 kiloparsecs, moving at 45 kilometers per second. Now, after this, I wanted to just briefly touch upon because I keep getting questions about, yeah, but there have been another, which is, it's a neutron star. So this was, after that time, the Lam et al., they published another paper, so here are their results. This was a little painful for me because this showed as if our HST astrometry, they do not fit the light curve, the fitted what you would expect from microlensing. As you can see, it kind of fits the north-south deflections, but doesn't fit at all any of the points in the east-west direction. Whereas here, if you measure it correctly, it really fits the expected one. So there they have two different models, and so the top one is the default model and the equivalent, the equal weight model, and none of these actually fits the actual data. So that's what they claimed that to be 1.6 to 4 solar mass. So I was wondering, how to handle this. So I was glad to see that, the Rose et al., they published another paper. It's better if somebody else does than me going and saying that we are right. That's not, it's much better if somebody else does this. So I was really happy that Rose and Udalski, Gould, they looked at this data. So the OGLE group actually re-reduced the photometry. See, what I did not go through is that there seemed to be a slight discrepancy between the path measured through astrometry and spectroscopy. Not really difference. The path, there was a correlation between the pi e and the other parameters. So we used the astrometry to break that correlation. So there seemed to be a slight discrepancy between the path that you derive from astrometry and photometry. So the OGLE group, they actually, Rose et al., they did re-reduce the photometry using a template taken in the best seeing conditions. Of course, the previous ones, the template itself was not necessarily taken from the best seeing because the best seeing ones comes later. So they took the best seeing condition images, the template, re-reduced, and that actually removed this discrepancy between what you derive from photometry and astrometry. So this is what we had derived from HST. This was the old one was here, and the new is here. So there is now no real discrepancy, except in the Lam et al. Model, where it's completely off. As I said, it doesn't really fit. So this is the new reduction, and that is pretty much consistent with what we had derived here before. The mass, distance, and velocity derived from Rose et al., they are consistent with our results within the errors. So, okay. So I have 10 minutes. I want to give 5 minutes at least for questions. So in the meantime, so that was the first update. In the meantime, 2 more epochs of HST observations have been taken, which extends the baseline to 11 years. We have reduced. I have not done the final figures yet, which in the process of being made now, and after we analyzed the values of phi from that you derive from photometry, astrometry remain consistent, and the results remain the same as before. So as you extend, the new ones fit the model quite well. So this is our result. So we detected the first isolated black hole, 7 to 8 solar mass black hole at 1.6 kiloparsecs, moving at 45 kilometers per second. Here is an artist's conception of the galaxy based on VLBA observations. So we are looking from up. So here we are here on this arm here, and we are looking down towards the galactic center. As we see, the black hole is on this Carina Sagittarius arm of the galaxy. So the black hole, 1.7 solar mass, 7 to 8 solar mass black hole on the Carina Sagittarius arm towards the galaxy. Now, the future, of course, we have HST, we have several more events, the longer duration events, which will come up soon. Then the Gaia astrometry will also lead to detection and characterization of a large number of astrometric microlensing events. VUCAS and group, they are working. So hopefully there would be several such detections. And Roman will, of course, simultaneously measure photometry and astrometry of a large number of microlensing events. Astrometry may not be enough. The Roman astrometry itself may not be enough to actually detect the black hole signature, but it will give enough sample for follow-up with their other, like VLT, HST, or KEK, so which should lead to detection of several black holes. The Roman will, Roman is the space-based telescope, which will simultaneously monitor photometry and astrometry will be the same as HST, so that can lead to the microlensing events. And the Rubin, the ground-based one, will provide a large number of microlensing alerts, which provide a lot of follow-up objects for further studies. And the VLT interferometry can, in principle, resolve the two images, which would provide a direct measurement of the theta e from a single observation. So in summary, astrometric microlensing is a powerful method to determine masses of isolated white dwarfs. We have measured masses of 2 isolated white dwarfs so far. The measurements are consistent with the theory of degenerate matter. The HST monitoring of long duration microlensing event, the OGLE 11462, led to the first unambiguous detection of an isolated stellar mass black hole. Combination of photometry and astrometry gives the lens mass to be 7.1 solar mass, distance about 1.6 kiloparsecs. There is a bright star, only 10 pixels, 0.4 arc seconds away. Its subtraction was critical for accurate astrometry, and that has been the main source for discrepancy with some other work. Its velocity is 45 kilometers per second with respect to the stars in that region, which suggests that it might have got a kick at the time of supernova explosion. So the future of astrometric microlensing is bright, as I showed you before. Now, I wanted to end, this was after we published, there was a lot of articles and all. One I liked very much, which I want to share with you. This was from Michelle Starr, science journalist from Australia. So he says, the black hole they found has a mass of about 7.1 times the mass of the sun. That would make its event horizon around 42 kilometers per second. Event horizon, the Schwarzschild radius is once Schwarzschild radius is about 3 kilometers per it scales with the mass, linearly with the mass. For 1 solar mass, it's about 3 kilometers. So that means for 7 solar mass, it would be 21 kilometers. So that means the size, which is the diameter, would be 42 kilometers. So this 7.1 solar mass of the sun, that would make its event horizon just 42 kilometers, 26 miles across. Take a moment to marvel at that. Scientists were able to detect an invisible object less than a tenth the length of the Grand Canyon from over 5,000 light years away by studying the changing light of a more distant star. That's freaking awesome. Thank you. So I wanted to finish at 10:55, and it's exactly 10:55. Thanks. Okay. Any questions?
Thank you, Kailash, a lot. We have time for questions now.
Yes.
it was so perfect that.
Everything is clear. Nobody has any doubts.
So I have a historical question for you.
Yes.
In 2000, you published a paper with Martin Dominic on astrometric microlensing.
Yes.
So have you expected then what was the future of astrometric microlensing? Could you imagine that we will be really discovering the black holes using astrometric microlensing?
Yeah, we had thought about that, but see, by 2000, even the HST, the technique was not developed yet to measure the 1 milliarc second. That method came out in the first paper was 2004, where Anderson and King, they developed a technique to be able to measure the astrometry to an accuracy of 100th of a pixel. Before that, 100th of a pixel measurement accuracy of astrometry had not been done yet. So in that paper, so yeah, thank you for pointing out. This is I think that paper, I'm very proud because I think that's where we first introduced, actually called it astrometric microlensing, where we told about Gaia and everything. We did not expect at that time that we have not mentioned there about HSTs because HST itself, the 100th of a pixel accuracy was not done. That came about 2000, 2004, 2005, after which immediately, of course, it came to me, and then we started by 2008, we started this, the program was approved because in 2005, already I think proposed, but it took the TAC a couple of years to accept our idea that yes, indeed, it is possible even. So yeah, that was the history.
Okay, thank you. Any other questions from the audience here at Warsaw? If not, then maybe Łukasz has some questions.
I have a question myself. I don't see other questions here on Zoom. So thank you, Kailash, for this. You mentioned JWST, and thinking about future, could you tell for a similar event like you showed here with a black hole, what would be the precision you'd expect from JWST? Is it so much better compared to HST that we will be able to see much fainter sources or more accurate?
Much fainter sources for sure, yes. So JWST gains not really in for bright sources, because you see the pixel size is about the same. It's a 6-meter telescope, but on the other hand, the observations themselves are at 1.2 2 microns. So the PSF becomes bigger. So it's not. If the source is bright, then you can achieve about same 100th of a pixel, not much more. What it gains is in two things. One, it can go to much fainter source, that's for sure. So here, if the source is much fainter than HST, the integration time becomes much longer, and then in one orbit it becomes very hard. So you can go to fainter sources. Then in the things like white dwarf, okay, there the gain is enormous, because what happens there is that you have a white dwarf which is much brighter than the background source, whereas as you go to 2 micron, then the white dwarf itself becomes much fainter, and the background source becomes brighter, which is much redder, becomes brighter. Not only that, there is no bleeding in the HST. The infrared detectors don't have such bleeding. So if there is more light, it just drills into that same pixel, but it does not bleed into neighboring pixels, which is a great advantage, because then the source remains unaffected by this any bleeding from the source. So that has a huge advantage. If you can actually avoid the bleeding from the neighboring star, then the precision becomes much higher. So for the ones like the white dwarf and all, the precision becomes at least tenfold, increases by tenfold. So, so the mass determination should become much better. We'll see, but yeah. So, yeah, hope I answered your question. Yeah, but the Gaia, should also give a lot of this. I'm sure you are working on this. Actually, I wanted to visit Warsaw. I wanted to discuss with you on this. Anyway, I'm sure you are working on that. So I'm looking forward to results from Gaia. Actually,
right. Thank you.
Łukasz, do we have any more questions from the online audience?
No more questions from Zoom.
Okay, then thank you all, and thank you, Kailash, for giving us the talk.
okay, great, thank you.